Okie doke. So we are going to kind of pick up where we left off. We were, guess I should do the slides. Um, we were working through this discodermalide synthesis, and we had gotten to the point where we had the aldehyde that is in the second line. So, and I wanted to specifically talk about the next reaction in a little depth, like the two steps from this aldehyde to this alkyne, because this is one, a name reaction, right? And two, it kind of uses two different reaction mechanisms that we have gone over thus far in the semester to get from that aldehyde to the alkyne. So, um, so you take triphenylphosphine and carbon tetrabromide and some base, and that makes this dibromoalkene. So this first step is effectively just the Wittig reaction, right? Where you make the Wittig reagent in kind of a unique way, right? Because you don't have, it's not like your normal steps to make a Wittig. And then you use N-butyllithium, THF at negative 78 degrees, and you do a lithium halogen exchange and then a deprotonation to generate this alkyne. So I wanted to go over the kind of the mechanism of this and the name of it. And so, okay, so that sequence is an example of what's called a Corey-Fuchs reaction. So there are some interesting mispronunciations of Fuchs that can come up. So it's Fuchs. So what this reaction is, kind of in its core, like the simple version, is it's a two-step procedure where you use triphenylphosphine and carbon tetrabromide to do a Wittig reaction to make the dibromoalkene, and then you use N-butyllithium, and then you have to quench it with something. We'll say water, and that will make a terminal alkyne, where the hydrogen on the end of the alkyne comes from water. So step one is a Wittig reaction that makes a dibromoalkene, and then step two, the N-butyllithium turns that into an alkyne. And I wanted to go over how you make the Wittig reagent, because how you make the Wittig reagent is kind of interesting and kind of illustrates some points. And then I wanted to go over the turning the dibromide into an alkyne, because it does use lean on some of the lithium halogen exchange chemistry that we've seen before, just to kind of show it all kind of come together. So the first part of this is we have to turn triphenylphosphine and carbon tetrabromide into a Wittig reagent, right? So and the way this happens is a little unique. It's a little different than what you would think, right? Usually, when we see a carbon with a halogen on it, we think we attack the carbon and push the halogen off, right? But why do SN2 reactions work, right? Part of the reason an SN2 reaction works is, oops, let's not discard that, is if you look at, right? The normal way, right? Normal Wittig. Okay. In a normal Wittig, you've got something where you have, like, let's say CH3 and just the bromine, right? The way an SN2, and it does an SN2 reaction. But why do SN2 reactions work? Because the bromide is partially negatively charged. It's pulled electrons away from the carbon, and it's made the carbon partially positive. So the carbon wants to be added to, right? Something like carbon tetrabromide, you have 4 bromines around it. None of those bonds end up being polarized, right? So you got these great big groups, and there's not a clear direction that the bond is polarized in. The carbon's a little positive, but you've not polarized any bonds. So what ends up happening here in the Corey-Fuchs is instead of attacking the carbon, the triphenylphosphine actually attacks a bromine and pushes electrons onto the carbon, which making a carbanion is usually super duper bad, right? You're usually not trying to do that. But when you've got a carbon that has 3 halogens around it, that carbon's short electrons, it doesn't mind getting a negative charge, right? It helps balance out the fact that it's got 3 halogens around it pulling electrons away, right? We actually did in organic 2, we did a reaction where you, was it the haloform reaction, where you put 3 chlorines or 3 bromines on a methyl ketone, and you can turn it into a carboxylic acid because the carbon becomes the leaving group. It's the same thing here. So we get this, and then this carbon with 3 bromines around it can attack the phosphorus. And then another triphenylphosphine. So that 3 got really squiffy. Another triphenylphosphine can attack, push electrons down, and kind of ran out of space. But in the end, you get triphenylphosphine double bonded to a carbon that has 2 bromines. So we kind of get to the Wittig reagent in a slightly different way than we normally would, right? We can't add to the carbon directly, so we add to the halogen, break the carbon bromine bond, get a carbanion that can add back to our positively charged phosphorus, then have another triphenylphosphine knock off the bromine to get us to our Wittig reagent. So here's our Wittig reagent. Great, this is our ylid that we need to actually do to react with the aldehyde. Right, so this first part here was just to make the thing to react with the aldehyde. Now that we have that, we have our aldehyde, we have our triphenylphosphine. Oops. And here we just do our Wittig reaction, right? I'm not going to go over the mechanism. We've done that pretty recently. So we get here. So we get to that. And then this is what reacts with N-butyllithium. So this is the end of step 1. Right, so this is the end of the triphenylphosphine carbon tetrabromide step. Step 2 you can sit down.
Thank you.
Sure. Step 2 is you have this dibromide and you treat it with N-butyllithium. So we know if we have a halogen and an N-butyllithium, we're going to do a lithium halogen exchange. That reaction is actually even faster than a deprotonation. So we will do a lithium halogen exchange. As you put it, we have at least 2 equivalents of NB lithium in this reaction. Right? Then our second NB lithium is able to actually, I should probably, let me fix where this lithium is. It actually matters. It should be over here. Sorry. Then we're able to use our NB lithium as a base, and it will grab a hydrogen and actually do effectively like an E2 elimination and remove hydrogen and bromine to make a lithium acetylide. Right, we end up with like butane plus lithium bromide. And then if we add water, next slide, if we add water to our lithium acetylide, you're able to make a terminal alkyne. What's nice is when we generate a lithium acetylide, when we have this, it's kind of squiffy, we have this, it doesn't matter what we quench the acetylide with. So, right, we learned in Organic 1 that, like, if you have a lithium acetylide, you can add a halide to it, right? And do an SN2 reaction and make a bond, right? You learned in Organic 2 that if you have a terminal, like an acetylide, you know, a carbanion, you can add an aldehyde to it and make an alcohol, right? It doesn't matter where the acetylide came from, right? It doesn't matter what you did to get to it. So in Organic 1 and Organic 2, we started with an alkyne and we treated it with base, right? This acetylide, even though it came from a dibromoalkene, is still an acetylide. So here, in the simplest case, you treat it with water and you make a terminal alkyne. But you can intercept that acetylide intermediate with anything that acetylide would react with normally, right? You go through all the steps and you have this acetylide, and instead of adding water, you could add an aldehyde and make an alcohol. You could add a ketone and make a tertiary alcohol. You could add an acid chloride and make a ketone. You could add a bunch of different things to get to that react with this. So when I was in grad school, someone said one of the faculty members said, never waste a reactive intermediate. So if you make an intermediate in your reaction that's reactive, you can try to use it to make the next bond. You don't have to just stop and then start a new reaction. You can just keep going. If you know in your mechanism, I have a thing I can react with, I should use it for something. So this, let me go back. So from like here to here is your basic Corey-Fuchs mechanism. Right? The reason I point out that the acetylide doesn't just have to react with hydrogen is in the synthesis that we're looking at, they don't actually have it react with hydrogen. They quench it with something else. So let me make sure I get the right silicon. Okay. So what they do is they have it react with, so they have their lithium acetylide, and it reacts with, I'm going to draw it out. Trimethyl chloride. So it adds to the silicon, knocks out the chlorine. Right, which is equivalent to, if they're just going to probably write like, I think I have it written as like silicon Me3. Right, so they add a silicon to the end of their alkyne. Oh, thanks, Crystal. My internet connection is unstable. Awesome. Thank you, Zoom. So going back to the slides, to the actual synthesis. So, right, they do the first step to make the dibromoalkene, treat it with N-butyllithium, they make that reactive acetylide, and then they add TMS chloride, and they get this alkyne here with the TMS group on the end. The reason they add a TMS group is they just need something that is big, so that will help like their next reactions with their selectivity, but they also need something that comes off. And carbon-silicon bonds aren't particularly the strongest, so you can get those off relatively easily. So they can put a big group on there, use it to direct their other reactions, and then later take it off when they don't need it anymore. If they put like a tert-butyl group there, you're not going to break a carbon-carbon bond easily. This is kind of a cheat at a tert-butyl. So, then they want to turn that alkyne into an iodide because they're trying to set up to do a palladium cross-coupling, right? So, yeah, I only know this because this is what my research group did. So this reagent here is called Schwarzer's reagent, and it does something called a hydrozirconation. It adds a hydrogen to one side and zirconium to the other side of an alkyne. Kind of like hydroboration, you added a hydrogen and a boron. Hydro, pick the atom name, do the same thing. So hydrozirconation, you add H to one side, zirconium to the other, and then if you add iodide, you replace the zirconium with an iodide. So it goes, I'll actually draw it. Like this is the awkward part, is just flipping back and forth between like whiteboard and slides over and over and over again, right? So you get your alkyne, and then you add H, zirconium, Cp2, right? And you get to something that looks like Zr and H. Yeah, sure, there are two Cp ligands on it, right? So this is just like a hydroboration, where it's a syn addition, right? The hydrogen and the boron stay stuck to each other, so they get added to the same side. Here, the hydrogen and zirconium are stuck to each other, they get added to the same side. So you know the double bond geometry that you're going to get based on the mechanism of the reaction. And then once you have this guy, you add iodide to it, and that zirconium is just removed to become an iodide. So that's all that does. And then if I'm remembering my names correctly that I taught you not too long ago, they then do a Negishi cross coupling where they take an alkyl zinc, palladium tetrakis, which is tetratriphenylphosphine palladium, and they replace that iodide with a methyl group. Right, so they had to take this alkyne and give themselves a handle so they could add the methyl group. This I actually had to look up. This is a way to remove a benzyl protecting group. It oxidizes the benzene, and then it causes the oxygen to fall off. It breaks that bond. Then the Sorin oxidation, everyone remembers this, primary alcohol to aldehyde. Look at all this stuff you guys already know. It's so great, right? You get your aldehyde, and they do a Corey-Fuchs reaction again, right? The Wittig reaction to make the dibromide, and then N-butyllithium. And this time, they quenched their acetylide with this ester so that they end up making an aldehyde. So I'll show you that because I said ester, and before we ended up making alcohols and stuff, so why is it an aldehyde? Right, So The ester that they use is a formal ester. So it's an ester that you get from formic acid. Right, so you have this ester, and then it adds, oops, red. Then it adds, kicks up. This is done at low temperature, because if you remember, at low temperature, you're able to have your tetrahedral intermediate get stuck and not fall apart. And then when they work this up and warm it, when they add a little bit of H plus, it falls apart and makes an aldehyde. So they use a Wittig reaction, or a variant of the Wittig reaction, the Corey-Fuchs reaction, on two different ends of the molecule, and they're able to turn it into kind of two different functional groups. And then they're able to use that to then, that's the middle of their discodermalide. If we go back a slide, right? That's the middle part of the molecule. Wait, not sharing with the people. There you go. That's the middle part. One second. Sorry, Zoom. Ah, so it's the middle part of their molecule. It's right here. So they're able to, the methyl group that they added from the Negishi cross coupling is this methyl group right here. And then the aldehyde becomes this alcohol at some point. And this is the double bond that was that alkyne that they just made. So that double bond right here in this alcohol are the aldehyde becomes the alcohol, this alkyne becomes a cis double bond eventually. All right, so the other synthesis is not a total synthesis, so it's not making the actual molecule. It's more akin to what I try to do, which is taking parts of a molecule off or changing it to understand how those changes impact the biological activity. So you can do it to try to make the synthesis easier, right? You're like, oh, this group's really hard to make the R stereocenter. What if we just don't have it? Do we need it? Because if we don't need it, it makes the synthesis way easier, right? Or what if we change this OH to a methoxy? Do I need that hydrogen bond? Is a molecule better or worse if I make this change? So you make analogs of molecules, you make changes to do one of two things, to kind of simplify the synthesis to make it so you can make them easier and without losing activity, or two, to understand what groups are important for activity so you can try to maximize the biological activity, so you can try to make them better or have a better understanding of how they work. So the Curran group, with Billy Day, they're both at the University of Pittsburgh. This is one of the projects that the Curran group did, is they worked on discodermalide, but they worked on removing kind of these stereocenters here. So this kind of chunk of stereocenters, and I think one over here, to try to make the molecule easier to make. Like, do we need any of these things? Let's find out. Because if we don't, like, setting all these chiral centers takes a lot of work. Like, you got to do a lot of specific steps. So we can get rid of some of them, and it'll make things easier. Right? So, and you can see here, like, they cut out. So here's the ring and ring. So right here, they cut out this alcohol. Like, do we need this alcohol? My life is easier if we don't have it, right? And then we have some other groups over here, double bond, right? They cut off this methyl group. Do we need this methyl group? Let's find, well, not methyl group, this here, all right. We'll get there. So I start here. They did, so we'll talk about this a little later on. So we touched really briefly in organic 2 on aldol reactions, right? Right towards the end, where it's like you have an aldehyde or a ketone and you make an enolate and it adds to another aldehyde. This is a special, this was, before this, they did an aldol, and they used this group here to impart the stereochemistry. Because if you just take like an achiral aldehyde and an achiral ketone and put them together, you make an achiral product, right? So here they used a chiral group to impart all the wedges and dashes that you see to make sure they were one enantiomer. So they take that off is the first step, and then they protect it with this. So this is similar to, so they make an acetal. They make this acetal here. And we had seen before when you made acetals, switching to the slide, to the whiteboard, right? So when you made acetals before, right, we did something where we were like, you have your diol, let's say, and it was usually you added an aldehyde and acid, right? And you made an acetal. They're not using an aldehyde, right? They're using another acetal, right? So they did it with this. LME, LME, and acid. So if you remember when we talked about we actually had a methoxy group on it, but whatever. That making an acetal is reversible, right? When you make an acetal, if you treat it with acid, it goes back to being the carbonyl group, right? So they use this acetal. They do this a few times in the synthesis. You get something that looks like this. I'm going to cut off some steps, but you'll. So you get something that kind of looks like a carbonyl, but it's activated, right? It's got a methyl group on it, so it's O+. So it becomes easy for your alcohols to add to the carbonyl carbon. So this is just a way to kind of cheat how you get to a C double bond O and have it be more reactive, as opposed to just starting with the aldehyde and only having a proton to activate it. Here, you have a stronger carbon methyl bond that just makes this oxygen more positive, because that carbon group's never going to come off. Like a proton's going to come off. Here, it stays on, because right, you protonate here, and then electrons come down, and that's how you make that guy. There's just a different way to get to the same kind of reactive group, right? To make an acetal, you need a C double bond O. Well, instead of starting with the aldehyde, they started with another acetal, and in the mechanism, you make a reactive intermediate. Make a reactive intermediate, and you react with that. So they do some protecting group stuff. So from this, TBAF removes a soluble protecting group. Iodide, imidazole, and triphenylphosphine turns an alcohol into a halide. So in this case, it turns the alcohol into an iodide. And then they add triphenylphosphine to make a phosphonium salt. So the step before a vinegar agent, right? These salts are usually pretty stable, so you can like make them and store them on a shelf. Again, like you usually will buy from a supplier, you'll buy the salt, not the actual illid, right? And then they take this aldehyde and then they treat this with sodium HMDS, which is a bigger version of LDA. So if you remember LDA, to the whiteboard. All right, share. Okay, so remember LDA is right, strong base, and it's lithium diisopropyl amide. That's LDA. There's a bunch of different versions of, I'm going to need more space, of HMDS. So the metal changes. You can have lithium, sodium, potassium, right? But it's still a nitrogen-based base, but you have two silicon groups, so two TMS groups. So this is like whatever the metal is, hexamethyl disilazane, HMDS. So it works like LDA. It's still a strong base, but it's got slightly different characteristics because it has silicons on it as opposed to carbons. But it's going to do the same thing. So if you see something HMDS, it's just a strong base. Right? And they do their, I have this drawn like they did in the paper. They kind of drew it a weird way in the paper. But you get your cis double bond from your Wittig reaction, just like you would have gotten normally. Right? This is a complicated Wittig reagent. This is a complicated aldehyde. But in the end, it still breaks down to that same simple aldehyde plus ylide with one group on it always makes a cis double bond. It still breaks down to that exact same thing, even though there's a bunch of fancy stuff around it. It's still doing that same core reaction. So they do one Wittig, and then they do a little bit of protecting group manipulation. So they take their acetal, and they're able to move the PMB group from, or PMP group, from being an acetal to being just a benzyl protecting group. So how does that work? So, oh, of course, I didn't give myself enough space because it's a giant. So PMP is para-methoxyphenyl, right? So this is PMP, right? And if you remember Diol is a reducing agent, right? It has one hydride. It can reduce aldehydes to alcohols, ketones to alcohols. It can reduce esters to alcohols or aldehydes depending on the conditions. But the thing that matters here is Diol has aluminum as the metal, right? So Diol is for diisobutyl aluminum hydride. So it has aluminum, and aluminum can be a Lewis acid. It can bond to, what's it called? It can bond to oxygens. So what happens here is, Belase on the radius again. You get your aluminum bonds to your oxygen and makes this positive. Try to do this right. So then, put it wrong way, wrong side. See, this is why you have to check stuff, right? This comes down. These electrons will come down and push electrons over here. So you end up with O, PMP, and then aluminum that's got a hydrogen on it. And then you're able to reduce that group. Does that make sense? So I kind of take the acetal and start to open it up like it was a proton. But instead of using a proton, I used aluminum that had a way to reduce the carbon-oxygen double bond that I make. And then that gets you to PMB, para-methoxybenzyl. and an alcohol. So it's a way, so again, you don't want to waste things that you've put in. So you've put in this paramethoxy phenyl group. Well, if you can just break one bond, it'll become a paramethoxy benzyl group that you can use to protect an alcohol later on. So instead of taking this whole thing off, right, removing all of this, making two alcohols, trying to then selectively protect one of the two alcohols to get to here, they were able to, in one step, deprotect the alcohol that they needed to use, but leave the other alcohol protected. Back over to slides. All right, and now, again, we have big aldehyde now. So they make the alcohol, then they do a Dess-Martin oxidation. Another thing that you already know. Look at how smart you guys are. Isn't this great? I'm a very good teacher. So you get your aldehyde, and now you have another vinaigrette, another phosphonium salt. You add base to it, and you make your next double bond. Right? So here they removed the OH and they removed this methyl group as the two changes they made that we can see thus far. Right? But they were able to go through and use two Wittig reactions to set those two double bonds. So they're going to put the molecule, big chunks of the molecule together using the Wittig reagent as a way to do that. So far, so good? Seem reasonable? So I know I go on these little tangents about reactions, and the reason I do that is like, I don't want you to look at like the synthesis and be like, I have no idea how, like what happened here. So this might like, it's something you now know, but like the big takeaway for us is the Wittig or like, things that are related to that. But I don't want you to look at this and just go like, I have no idea how we got from here to here. Like it's important that I take a second and show you, right? And like at some point, if you're reading a paper, not even like in organic or something, right? Like if you, whatever field you go into, right? If you get to something that you don't know, right? Usually then you have to take a second and go down the rabbit hole of following some references and figuring out like how that actually works. So you don't feel like lost in that step. And so I'm kind of doing that for you where it's like, I know you don't know how this works. Let me show you a quick explanation of how it works so it makes sense. The problem now is like when you go down a rabbit hole, you're always like 2 clicks on YouTube from the Illuminati. Like it's just like you're just right there. It's like, Khan Academy to this to the Illuminati you're watching. And it's like, how did I get here? Like why was my suggestion from like the Wittig reaction, the Illuminati? How does this work, YouTube? Explain your algorithm to me. All right. So there's a variant of the Wittig reaction called a Horner-Wadsworth-Emmons reaction. And the big thing here is instead of having two phenyl groups, you have this phosphonate ester, or three phenyl groups. You have this phosphonate ester, and you always have a carbonyl group on the other side. Usually an ester, but it can be a ketone or aldehyde depending on what you're trying to do, or an amide. And these are normally selective for trans double bonds. You can do some things to change the selectivity. So here you get the cis double bond because you add something called 18 crown 6. So there's this group of compounds. They're called crown ethers, and 18 is how many atoms there are in the ring that make this ether up. And then the second number, like 18 crown 6, is 18 atoms in a ring, and there are 6 oxygens. That's the 6. And they are, and the different crown ethers are specific sizes that grab certain atoms. So 18 crown 6 is the right size that it will go grab a potassium. I think the sodium one is 15 crown 5 is the one that specifically goes and grabs sodiums. So here, if you run this reaction, but there's no metal available to interact with the anion, you make the cis double bond. If you don't have that crown ether and you do the exact same thing, you get the trans double bond. Right? If you put a group here, you get the cis double bond. What is the difference here? Oh, what is the difference? Oh, the different sizes of methyl versus isopropyl, you change your selectivity, right? So you make your group bigger, you get more trans double bond. You use benzaldehyde in 18 crown 6, it's trans. This one's hard to switch. But here, so you go from methoxy groups to CF3. This is a different reagent. When you have trifluoroethanol as your group, this is the Stilgenari variant of the Horner-Watson limit. I'll talk more about it in a second. And it always selects for the cis double bond. General rule, Horner-Watson image reagents act like stabilized ylids from Wittig reactions, and they typically want to be trans. That is kind of their default setting, and you can tweak things with them to make them cis, kind of like we saw in the Wittig reaction. It wants to be cis, but I can tweak things and I can make it trans sometimes. Here, these want to be trans, but I can tweak conditions and be cis. The major tweak, the thing that you do the most, this is a really bad angle on me. Sorry Zoom, but this is what you get. I just looked down and it's just like up under my chin. I just need to hold a flashlight and tell spooky stories. I mean, I'm sure organic chemistry slides are spooky stories, but whatever. But the main way you can make a Horner-Watson image reaction make a cis double bond is by putting 3 fluorines on your ester group, on the O. So having this as your ester, this OCH2CF3, that makes them cis. So default, they want to be trans. Add 3 fluorines onto your ether part of your phosphorus. That will make it cis. That's kind of the shorthand of it. So the way these work is, here we go. This is what I had to redraw last night. So you have your, you can see here. Let me take a second and draw something first before I go into this. So what ends up happening basically, right, in the shortest, simplest way for, I'm going to misspell this. Corner. Is in the simplest case, you have RO, got 2 of those guys, phosphorus, and then you have some ketone, ester, aldehyde on the other side. And you treat this with base. These 2 hydrogens right here are very acidic because they're between 2 effectively carbonyl groups, right? So if I treat this with base, I'm going to make an enolate, right? And this enolate is stabilized, right? Because I can draw another resonance structure where, actually make it so you can see the arrows. Where, draw right. Where you could kind of see the double bond being over here. Right, so R1. So that enolate, that carbanion can move between the two oxygens, right? I have two possible structures for it. So it's a stabilized anion, right? It has extra resonance structures. So what happens is you take your Horner-Wadsworth Emmons reagent, you make that enolate, and then it does effectively what amounts to an aldol reaction, right? So right, and then I have some aldehyde, whatever. We come down, add to the aldehyde, kick electrons up. We get something that looks like this. R2 and R1. And then I make what looks like the same oxaphosphatane that we made from a Wittig reaction. So now, right, phosphorus loves oxygen. I've got this negatively charged oxygen beside a phosphorus. That's going to add, we're going to skip a step to make this easier to see. Right, you're going to get something that kind of looks like this. And then this will fall apart. These electrons will go here. These electrons will go here. And you'll make, normally, a trans double bond. So that's kind of the base mechanism. And that slide that I put up for a second, that looked super busy, has kind of explains the selectivity, how you get E versus E. And so I need to show you the basic mechanism before I hit you with the thing. So does this make sense? You're just getting to that O minus in a slightly different way than you did from like the base Wittig mechanism. But you get to that four-membered ring, and then it falls apart, and you get your trans double bond. So why does it typically select for a trans double bond as opposed to a cis double bond? Whoop. And that's because just like in the Wittig, remember we said that that having a stabilized ylid in a Wittig, you get the trans double bond because it goes through like a late transition state, and it can try multiple times. Okay, share. So this right here, this and this, are examples of what are called Zimmermann-Traxler transition states, which are you are able to model how the nucleophile, the thing that's adding to the aldehyde, and the aldehyde interact by making a six-membered ring, by making a cyclohexane chair, where the metal, whatever metal was on your base, is bound to the oxygen of the enolate and then coordinates to the aldehyde, right? And then so that holds those two molecules together, and it can kind of wrap around like they're a chair. And then the last little bit here is this is the carbon that's going to add to the carbonyl carbon of the aldehyde. So that makes your six-membered ring is you kind of have these two like weak interactions that are the oxygen being bound to the metal, and then they kind of curl around, and that last part of the chair is that bond that's going to be formed. You've got the double bond of the enolate has to line up with the carbonyl carbon to add to it, and that gives you your six-membered ring. So the top pathway here is the kinetic pathway. If you remember, again, being under kinetic control is whatever thing you make fastest is the thing that you make the most of. And then thermodynamic control, you work to make the thing that is most stable, right? So under kinetic control, you use the low energy chair conformation where the R group on the aldehyde here is equatorial and doesn't bang into this methoxy group, right? That forms this product, which if you make a Newman projection, you're welcome. When your O minus adds to your phosphorus, you end up with your two hydrogens line up. They're on the same side. Your R group and your methoxy group line up. They bang into each other. They have like a gauche or an eclipsing interaction, right? They have a gauche interaction here, but they end up kind of eclipsed. So even though that's the less stable Newman projection, it works and you get the cis double bond. So this is the low energy reaction, the low energy, I can say low energy enough, it'll make sense, right? So if you remember activation energies, right? Your kinetic product always had the lower activation energy, right? That is the low energy chair conformation here, right? R group is equatorial, that's lower in energy, so that's going to form faster, right? But if your R group is axial, that's higher energy, but the Newman projection you get, right, you get less. This R group is no longer between two non-hydrogen groups. It gets to be between a hydrogen and non-hydrogen group, right? So I end up with something that has less gauche interaction, so it's slightly more stable. When I have my methoxy group add to my phosphorus, instead of having hydrogen, hydrogen, big group bang into each other, it's always hydrogen in a larger group, right? So I don't have as bad of an eclipsing interaction. So that's lower in energy. And what I end up making is this hydrogen is on the same side as this R group. This hydrogen is on the same side of this methoxy. You end up with a trans double bond. So the kinetic pathway, I get one shot at it, and I make the cis double bond. The thermodynamic pathway, if I set up thermodynamic conditions, right, I'm going to get both of these, but they're going to be able to, I'm going to go through both these pathways, but the kinetic pathway is going to get like here, and it's going to go, oh, I can do better, and it's going to go back, and it's going to eventually funnel down to the thermodynamic pathway. So if you set it up that you favor the kinetic pathway, you make the cis double bond. If it's set up that you favor the thermodynamic pathway, you make the trans double bond. The way that we do that in Horner-Wadsworth-Emmons reactions is the kinetic pathway, you put that CF3 group on the phosphorus, and that favors, once you get here, I'll have to draw it here in a second. Once you get here, if you have electron withdrawing groups on the phosphorus really wants to ditch an electron withdrawing group and get electrons from another oxygen. As soon as you get here, it snaps closed, makes a cis double bond. If your phosphorus is more electron rich, doesn't have those groups pulling electrons away from it, it's willing to go, I could probably do better and make a more stable compound, and it will do the reaction again. So changing that group on the end changes whether or not you're under kinetic control or thermodynamics. So let me actually draw it, because I know talking is no good. So when you have this, so generic kind of the stock thing is CH3, CH2, two of those on your phosphorus. So you're going to be under thermodynamic control when you have just like an ethoxy on your phosphorus. And that's going to favor you making the trans double bond. If you have CF3, CH2, there's a phosphorus there. This is kinetic control. and your cis double bond. So just changing the ester group on your phosphorus changes whether or not you're under thermodynamic control and making trans double bonds, or if you're under kinetic control and making cis double bonds. So just changing this group is all it takes to change that. And the reason is this is electron withdrawing, or more electron withdrawing than just the ethoxy. And when you get to that weird Newman projection, it doesn't have a chance to go back. The phosphorus is so reactive, it just snaps closed and spits out the double bond. When you have just the ethoxy group there, when it gets to the Newman projection, it can take a beat and go like, I can go break apart again and try again and see if I can make something more stable. Whereas with this, it just goes like, I got to react. I got to go. Whatever I get, I get. I just got to get this done with. Right. So here, when this has a CF3, snaps closed, cis double bond. When it has just ethoxy, it can go back, try again, and so you make the trades. So I wanted to take a brief diversion from all of this to talk about these transition states for a second, these Zimmermann-Trachsler transition states. This was the placeholder slide for, I had to go back and make the slides. I was like, I don't know if I'll do it, but I had time last night, so we got it done. So Zimmermann-Trachsler transition states, they were initially developed to explain the stereoselectivity in aldol reactions if you ended up with your alcohol and like your carbon group on the same side or on opposite sides, right? And so you just model your transition state like it's a chair in a cyclohexane, right? And your goal is to kind of minimize A1-3 interactions and make like the most stable chair you can make, and then that's going to tell you how your groups are arranged in the chair isn't how they end up being arranged in the product. And there are, even though it's for aldols, there's a lot of things where you end up just modeling your transition state like it is a chair and using kind of your inherent knowledge about like what group should be equatorial, what group should be axial, and that will allow you to predict what your product's going to look like. So they don't all get to be called Zimmermann-Trachsler transition states, but this is kind of like the genesis of that idea of, hey, make your transition state a chair and then use that. So the kind of the classic for Zimmermann-Trachsler transition states is you make an enolate and you have two different enolates you can make. You can make the Z enolate where the oxygen in whatever carbon group on the other end of the double bond are on the same side, or they're on opposite sides, right? So Z double bond, E double bond. And then you react with an aldehyde and you make your aldol product, your beta hydroxy ketone. So the favored for the Z enolate, you have your methyl group ends up being axial and your R group on your aldehyde ends up being equatorial. So these are on the same side, right? They're both back. And that works out to that your two groups end up on your methyl group that's from here is back, right? And this is down. It ends up down. And then you got to twist the bond a little bit, but then your oxygen here ends up back as well. So you end up with this cis product, right? And then if you put the two groups axial, oh no, what's that? This is what happens when you do stuff at 10 o'clock at night. You forget to change something. Or you change the wrong thing. 1 second, we're going to fix it. In the words of the old original memes, Bill O'Reilly screaming, "We'll do it live!" So we're going to do it live. We're just going to fix it real quick. Uh-huh. Okay, we fixed it. We were off one dash, but we're good now. So I just made the enantiomer. Stop giving me design suggestions. PowerPoint, we got this. There you go. PowerPoint. There we go. And then, gotta share this with Zoom, which since I'm bad at this means I have to share like 3 different things first. We'll share that, and we'll make this big. Thank you for bearing with me, denizens of Zoom. And then we're gonna share this guy. Sure. Ah. So here, these are on the same side. Then here they're on opposite sides, but they have 2 groups that are axial. So when you have the Z-enolate, you don't make the trans product, because to make the trans product requires you to put 2 groups axial in your 6-membered ring. When you have the Z-enolate, you get 2 groups that are equatorial. That leads, this group is up, this group is down. They're on opposite sides. They end up on opposite sides in the product. If you put them both up, so this R group is now axial, you'd make the cis. So you don't make this because you get an axial group versus having 2 equatorial groups. And you don't make this one because you have 2 axial groups. So you can put your groups on the chair and then predict this chair's lowest in energy. How is that going to make my product look? Now, we can later go over how you kind of like get from the chair to the straight chain thing. But I just wanted to show this is kind of how you use it as you look at your chair. You're like, okay, which groups are axial, which groups are equatorial, and then you can translate that to the actual product. Okay, distraction over. So, back to Horner-Wadsworth Emmett reactions. So, for generalizing these reactions, you get Z double bonds when you have rapid cyclization of the oxophosphate intermediate. So when we get to like here and here, if once you get here, this cyclizes really fast, that's going to be under kinetic control. That's going to make your Z double bond. Oh, keep going. All right. So you get that also is reinforced by using big counterions that don't bond to oxygen really tightly. So you get an O- that is more reactive and more likely to add to that phosphorus, right? If you add things that bind your metal, like 18 crown 6, like we saw before, right? So when you have a counterion, when you have a potassium, a sodium, a lithium, right? Their job in the reaction a lot of times is they just bind to the negatively charged thing to balance it out, right? If they get the tighter they bond to the negatively charged thing, the less reactive that negatively charged atom is, because it's being balanced out by a positively charged thing, right? But if you have a big group, a big counterion, they don't bind really tightly to anions because they're big. And then if you use something that goes in and grabs that ion and kind of pulls it out of the reaction, you end up with your negatively charged thing being bare, just being a bare, in this case, alkoxide, an O-, that is just bare, just an oxygen with a negative charge, nothing to balance it out. It's more reactive that way. When it's more reactive, it's going to react quicker, kinetic control, right? And then making the phosphorus more reactive by adding your CF3 group, right? So you can force it that way. So you can see here, if my R group is methyl, I favor the trans double bond. If my R group is trifluoroethyl, I favor the cis double bond. So even with the base and everything being the same, just changing the group on the phosphorus totally switches my reaction selectivity. to get E double bonds, right? Strongly coordinating metal ions, sodium and lithium, they're smaller. They're similar in size to oxygen, so they're going to bind that oxygen more tightly, right? So if you make the groups around your phosphorus bigger, you're going to destabilize that thinking. You're going to destabilize the kinetic pathway, get it closer in energy to the thermodynamic. So that's going to make it so you do less of that. And then if you have less reactive aldehydes, they're going to be more apt to be able to go back to the starting materials. If you go down the kinetic pathway, they can go back easier and then find their way to the thermodynamic pathway. The big thing though is just changing from just putting that CF3 group over there. That's the thing that, like, when you see that, you go, oh, that's going to make a cis double bond. So I picked another discodermalide synthesis to kind of illustrate how someone else kind of approached the molecule. That first one I showed you, they did some cross couplings and some Corey-Fuchs reactions. Here, they're actually making a Horner-Watson-Emmons reagent, and they're making the still Gennari variant where they have the fluorine on there because they want to make a cis double bond. Let me go back a second to show you what double bond I'm talking about. Should I put discodermalide in here again? So this double bond right here, this cis double bond, that's the one they want to make with the Horner-Watson-Emmons reaction, right? Their whole kind of point of their paper was they said, hey, people make this double bond all the time with Wittig reactions, but their selectivity, their E to Z ratio isn't great. Maybe it's 5-to-1 or 6-to-1, which sounds pretty good, but if you think about what ends up happening, is like if you make a gram and you have a 5-to-1 selectivity, that means that you get to keep like 860 milligrams is what you want, and you throw away 140, right? That's not great, right? If it's 20-to-1, you get to keep like 950 milligrams and you get rid of 50, right? That's way better. And in a synthesis this long, you might be doing this step on like 10 grams worth of stuff. And so you don't want to have to just always throw away 1.5 grams or 2 grams of material because it's the wrong selectivity. So they were like, we want to do this so we use this version so we can get a better reaction. So again, same kind of trick to make the acetal protecting group, right? They started with an acetal and they trapped this diol as an acetal. This is a DDQ is a way to take off these paramethoxybenzyl groups. Get you the alcohol. They oxidize this. So this oxidation, DMP, Dess-Martin pyridine, goes to an aldehyde. This is just bleach, and this will oxidize an aldehyde to a carboxylic acid. So you guys learned, I taught you guys the like old school, like super sledgehammery, like Jones reagent, where you're like mixing chromium oxide and sulfuric acid together, right? You have to be super brave to be like, yeah, I spent like, I don't know, 2 months making this. I'm gonna throw some sulfuric acid at it. Like that's just a level of like bravery and stupidity that most people don't have. So like there's a lot of different ways to do those oxidations. So like I taught you guys like 3 ways to do the oxidations. There are probably 50 or 100 more just because of when things get more complicated, you have to take into account more possible interactions. But this takes that to an acid, and then they turn that acid into an ester. Now, the way we learned how to turn acids into esters, let's find the thing, right, was we took the acid, right, acid to ester, right? We did stuff like Fischer esterification, where we took an acid and we were like, hey, we're going to take methanol going to take some sulfuric acid, and we're going to heat this up, and we're going to make the ester, right? And you take, right, this OH leaves, that oxygen goes away, becomes water, right? And you add the O, and you add all of this, becomes all of that, right? The way they did it is they took the acid and they added, oops, I do have an extra hydrogen. Let me check. I do. So they use something called TMS diazomethane. And they keep this oxygen. They basically use the acid as a nucleophile. So instead of adding to the carbonyl carbon with another alcohol, they keep their oxygen and they use this oxygen, this lone pair, to add to that carbon, and they then push off nitrogen, right? This is a really good leaving group. And then they lose the TMS group or whatever, and you end up with your ester that way. So in the way the Fischer esterification, your alcohol adds to your carbonyl carbon, and you switch off the oxygen from the acid with the oxygen from the alcohol. Here, your acid oxygen adds to the carbon. Now, diazomethane, CH2, blows up like all the time, to the point of you have to buy special glassware. So you know how all of the glassware that you guys use in lab like fits together and has those ground glass joints? You have to buy glassware that doesn't have ground glass joints, because the friction of two ground glass joints going together causes this stuff to blow up. So they put the TMS group on there, so it's just a little bit less boom, but it's still scary AF. Reagent I never used. I've heard stories. I'm just like, no, I'm good, thanks. Right? So the general rule of thumb is, if like the closer your ratio of nitrogens to carbons is to being at 1, right? If you have 1 nitrogen for every 1 carbon, your thing's probably is going to be a little explosive. Here we've got 2 nitrogens for every 1 carbon. Boom, no good. So they add the TMS group, so there's a few more carbons, so it's just not all boom. It's like, I don't know, 30% less boom. But they're making their ester in a slightly different way, as opposed to having your alcohol add to the carbonyl carbon. You're adding your oxygen from your carboxylic acid to an electrophile. Oh, and we'll end on boom because it is 10:40, and my headphones are dying. So perfect timing. So people of Zoom, I will see you when I see you. I guess like 2 of you, 3 of you in lab. So I will see you guys in lab. Thank you.